And then we compare the imaginary part. We have the r times sine theta equal to s to nth times sine of the n alpha. And then you cancel these two r's from the both sides because the s to nth is equal to r. Then you have the sine theta equal to sine of the n alpha. Now let's draw the terminal side of these two arguments on the unit circle. So now this is the point on the unit circle. Okay, this is the terminal point of this terminal side of this angle on the unit circle. So we know by the definition of this angle, this guy should be equal to cosine theta and sine theta, right? And also this is same as cosine of n alpha and the sine of n alpha. Okay, so that means both the theta and the n alpha have the same terminal side. Okay, and we know two angles have the same terminal side, they are coterminal, and their degree measures just differ by the multiple of the 360 degrees, right? Or see the real measure differ by the multiple of 2 pi. So we have the 2k pi plus theta equal to n alpha. So this k is a integer, positive or negative. Then from here, we divide both sides by n, we get alpha equal to 2k pi plus theta over n. And by the fundamental algebra theorem, we know x to nth equal to z. Here the x is unknown, z is a known number, has exactly n roots. So now we just need to let the k equal to, so we let the k equal to 0, 1 to the n minus 1, let k be this n integers, then we can find the arguments of those n roots. Okay, and you may want, if we take m to be the n or the n plus 1, what will happen? Let's see. If I let k equal to n, let's see what we get. So in this case, we know alpha, this is argument of the nth root of the z. Let's go back to review. So I will define this nth root. So first we have this constant number, right, which is in this trigonometric form. And then we let a plus bi be the 1nth root of this constant number, right? So we have this equation. Then this alpha is just the argument of the 1nth root of this constant number, right? So right now we can take the n arguments for all those n roots of this complex number. So now, let's see what happens if we let k be n. And by the formula, alpha is equal to 2k pi plus theta over n. Then this guy, k is equal to n. So we have the 2n pi plus theta over n. Now this is just equal to 2 pi plus theta over n. And we know this guy coterminal with the theta over n. So this just corresponds to the case when we let k equal to 0, right? You see here, if we let k equal to 0, then we get a theta over n. So if you let the k equal to n, then you just get one of the roots you already got by letting k equal to 0, 1 through the n minus 1. And let's see what happens if the k equal to n plus 1. So if the k equal to n plus 1, then alpha is equal to 2 times n plus 1 times pi, right? We just replace this k by the n plus 1. And then plus theta. And then over n. So now this guy is equal to 2n pi plus pi plus theta over n. Now we divide these two terms by this n. The first guy, 2n pi divided by n, you have the 2 pi. And then second part, you have the pi plus theta over n. So we know this is coterminal with the pi plus theta over n. And this is just case when we let k equal to 1. Go back here, you see, if we let the k equal to 1, we have the 2 pi plus theta over n, right? So, hold on. Oh, here's 2. That's right. We should have the 2 pi here. 2 pi. And also 2 pi here, not the pi. Okay. So we have the 2 pi plus theta over n. And this is just case when we let the k equal to the 1. So that means from these two examples, you can see if you let the k equal to the integers other than 0 through the n minus 1, you just get all those roots you already got from this n integers. And by the fundamental algebra theorem, we know we exactly have the n roots, and this this n integers just give us all those n roots. So now the nth root, totally we have the nth roots of this z equal to r times cosine theta plus I times sine theta is given by this expression. First, we know we read this nth root in such trigonometric form, right? This a plus bi is supposed to be the nth root of the z, and is equal to s times cosine alpha plus I times sine alpha. And what is s? S is equal to the nth root of r. So first, let's get s, the modulus. So we have the r to the 1 over n. And then we get argument. How do you find the argument alpha? See, we use alpha for the argument of this nth root, right? And then later we find the expression for the alpha. And alpha is here. Okay, go back to here. So alpha is here, 2k pi plus theta over n. So let me write down this here. Cosine of the 2k pi plus theta over n. And then plus I times sine of the 2k pi plus theta over n.